Can you guys hear me?
Yes, we can.
Okay.
Yes, please.
Okay.
Yeah, let's give them.
Yeah, some few minutes because people are
Yes.
trying to get in, so let's just give them some 5 minutes to really join.
Yeah, I agree.
Sounds good.
Agree.
Welcome to another.
On TikTok. Okay. No channel. I thought like a TV channel.
How do you say send me in person?
Nitumie
Pesa. Is it what is that? I'm in trouble. You're sending me half.
Dominic, you're on mute.
Okay, thank you. Welcome to another technical session by SPE Ghana. Today we have a distinguished personnel in the field of flexible pipes who are going to present to us the solutions these flexible pipes offer to us in this industry. But before we begin, I would like to call on Ghana's section chair, Sheena, to give us an opening remarks before I introduce the speakers for the session. So Sheena, over to you.
Yeah, thank you, Dominic. Can you hear me?
Yes, loud and clear.
Okay, good. Good afternoon to everyone, and thank you so much for making time to join us on this call today to learn about how flexible pipe technology can add value to energy sustainability. I want to also thank our speakers, Donald Panty and then Jose Vegara. Donald, I've known for more than 13 years now when we all started working in Baker Hughes. I'm always filled with a sense of pride whenever the people that we started this industry in today turn out to be the experts we invite on our programs to share what they know for us. So I'm very happy to have him here, and I hope you're all ready to learn about this new technology and then take good notes from it. Thank you. Over to you, Dominic.
All right. Thanks, Sheena. Thank you for brief introduction. I would like to give a brief background of our presenters today. Today we have two mechanical engineers who are going to speak to us on flexible pipe and its application in our industry. They have a combined experience of over 30 years doing various things in the oil and gas industry. But I will start with the profile of Jose Pinto. So Jose is a strategic result-oriented mechanical engineer with qualifications in operations management, business development, sales, marketing, HSC, and quality systems. He also has knowledge and experience in gas lift, maintenance, flexible pipe selection, operation, and installation. He has over 17 years of experience overall in the industry, as well as knowledge about this flexible pipe. So he'll be speaking together with Ronald Panty. And as Sheena said, Ronald is part of us. He was part of the Ghana SPE before he joined Baker Hughes America. Ronald has a seasoned mechanical engineer with over 13 years of experience.
Yeah, there aren't more.
Kindly mute yourself if you just joined us. Thank you.
Full fast. And also reduce stress.
All right, thank you. Ronald has been with Baker Hughes since about 13 years ago. He's done a lot of experience spanning from field operations, applications, business management across multiple upstream disciplines. He has held multiple operations and management roles across 4 continents and has been recognized for professional leadership and operational excellence. He also mechanical engineering and an MBA from Texas A&M University. He's currently the North American Service for Flexible Pipeline Systems in Houston, together with Joseph, giving us an insight into the operations of flexible pipeline and the solutions it offers us. So over to you, Claude, and Joseph, the audience are ready for you.
All right, thanks a lot, Dominic, and Sheena. I mean, I appreciate the that introduction, I guess. And again, on Jose's and my behalf, you know, it's a real pleasure to speak to everyone here, and thank you for taking some time out to join us for this presentation. Right. So for today's topic, we're going to give a brief exposition into flexible pipes, looking at composite materials being used for this product, and also look at the value proposition in terms of CCUS and you know, the long-term benefit it offers for energy sustainability. So we'll just have a brief overview of flexible pipe, looking at its applications on onshore and offshore, and go into the technology review, which Jose will kind of enlighten us on about a little bit more. And we'll look at the value proposition in terms of its application for CCUS and the overall benefit for the circular economy, looking at the carbon footprint reduction, right? We will look at some case histories as well. And we'd like to take some questions and offer some answers at the end of the presentation, if that's okay. Okay. So just a brief history. I'm sure a lot of us here might know, you know, pipelines have been used as far back as the 500 BC for land applications. Early record of pipeline applications was from bamboo in China, mostly for transport of oil and heavy crude from well sites to, you know, for commercial and domestic applications. Now the industry transitioned to pipeline in the 1800s. You know, when an individual looked at using barrel muskets from guns to bring gas from his well to his home, and you know, in this application they were welded together as we currently do. And again, you know, this process has been commercialized mostly for onshore. From an offshore standpoint, you know, the first application of flexible pipe that we've seen, even though Sheena mentioned it is new technology, you know, just wanted to highlight that, you know, it's technology that came, you know, as far back as World War II. There was a project in World War II dubbed a Pluto, which is an acronym for pipeline under the ocean. I'm going to play a quick video here for a few minutes just to give us some background. Okay.
Pipeline under the Thames.
Are you getting the audio?
Yes. Yes, we're hearing the audio.
The invention and manufacture of the lifeline, which carried petrol for the Allied armies in Europe, is a work of genius. Tribute is due to Mr. Geoffrey Lloyd, Minister in charge of the Petroleum Warfare Department. Constructed somewhat like a submarine electric power cable without the cores and insulation, this pipeline makes engineering history. The central tube is wrapped in layers of bitumen, paper, cloth, 4 thicknesses of steel tape, jute, steel wire, and still more jute. Two 30-mile lengths were made first, with a 2-inch inner tube. After intensive tests, the carrying capacity went up, when the diameter was increased to 3 inches. The pipeline was proved equal to working pressures of more than 1,200 pounds to the square inch. The finished cable is loaded into circular tanks built into the converted coasters and tankers, which are to take it across the channel. From the holds of these ships, like some fabulous snake-like monster, the pipeline begins its cross-channel trek. First laying tests were carried out in the Bristol Channel at the end of 1942. Though they didn't know it, petrol users in Devon and Cornwall were running their lorries and cars on petrol pumped underwater from Swansea to Ilfracombe. The D-Day pipeline reached the opposite shore safely. It was scheduled to carry a continuous flow of petrol deep into Germany, direct from tankers unloading at British ports. Another variety of pipe was...
All right, so, you know, those of us who are war historians, I'm sure will enjoy this, and you have an opportunity to look it up. It's available on YouTube. You can access it for just to get some more insights into the project. But again, like I said, it was a supply chain project. Main challenge, you know, during that war time was you know, access. The axis was not, the axis side of the war was not allowing ease of land transport, whether by sea or by road, right? So the main aim of this project was to transfer fuel from Britain to the shores of France during that Operation Overlord. And you know, this innovation came in handy, right? But in a nutshell, you know, what we wanted to highlight here is, you know, the polymers, as you can see, they used, you know, paper, jute, tar, and different materials to create the flexible pipe and offer that same level of mechanical integrity. But the polymers have evolved, right? But the assembly process remains the same, which you will see in some slides, some further slides along. Okay. Right. So, you know, one would ask, right? So from an organizational standpoint, you know, Baker Hughes has been in this business, just ventured into this business through acquisition, right? We acquired a company called Wellstream in '83 that had a long-standing experience in the offshore space, developing this type of products and delivering the associated services. You know, business expanded on the offshore side, where we have a logistics and operational base in Brazil that, you know, supported this business segment. And we later introduced a carbon fiber composite material, which, you know, further was used for offshore applications, for high pressure, high temperature type applications. The company later acquired a company called Polyflow, which was more an onshore thermoplastic products business, and that product line was further expanded with a composite product line offering, and it's something that we offer extensively in the US today. We have a ongoing JV with our non-metallics department with Saudi Aramco, looking at the application of these flexible pipes, composite material, for multiple installs, from you know, from carbon sequestration to just plain oil and gas supply from wells in that area. And we do have a manufacturing plants currently in for the onshore application currently in the US, and a manufacturing plants as well in Newcastle. And then we are undergoing API qualifications for the JV that we have, for the JV that we have in Saudi Arabia. Okay. Right. So again, in terms of application, right, the application is vast, right? Like we saw earlier, from a supply chain, supply of fuel in a war scenario, it can be used. The flexible pipe is not only limited to oil and gas, can be used in mining for dewatering, underground mines, and just for any kind of gathering and fluid consolidation, right? From a CCUS standpoint, you know, carbon capture, a lot of us are aware of the concerns with CO2 emissions to the environment, and flexible offers some value in that space, which we'll talk about in a little bit more detail. Hydrogen generation is another aspect that we support, desalination and rehabilitation, which is a critical one, right? Because it's good to highlight the fact that, you know, the total install base of pipeline is predominantly metal, right? And then the challenge with metal, which you see over the next couple of slides, is the ability to easily accessed and repair over time, right? As they begin to degrade. So I mean, this schematic just shows, you know, a typical oil field infrastructure and how the pipeline kind of offers that transport opportunity at ease. Okay. Jose will take us through an overview of the technology itself. Okay.
Yeah.
Yeah.
Well, good afternoon to everyone, right? Let's speak now about what can be seen in the market, right? It is important to remark that there are different types of pipes available in the market, which in concept are flexible pipes, right? So we have conventional HDPE, which is well known by everyone. We know also the glass fiber pipe, which in somehow is flexible, right? They have certain level of flexibility. We also have the RTPs, which are these pipes shown here, which are defined as reinforcement thermoplastics pipes. And then we have CTP, which are composite pipes, right? So there are a wide world of different kind of technologies available, right? And the idea is that we will bring some of what can be available, at least on our company, for you to know what can be seen in the market. The first example is a low pressure pipe, which is PE Flex. This kind of pipe do not have a reinforcement. So is basically, as we can know, a conventional pipe, HDPE, but it's reinforced internally with a nylon liner or a PPS liner. We are going to speak about the polymers that are being used to protect the pipe in few seconds, right? But the point here is that, as you see, the difference between this product with the mid-pressure and high-pressure product will be related with the amount of pressure that this product can stand based on the reinforcement that is included. Let's move on thermoflex and composite pipe. The difference with this product against the first one is the ability to carry on more pressure at different ratings, and this is related with the type of reinforcement that is being used. In this case, for example, in our company, we use aramid fiber in the case of thermoflex. In the case of composite pipe, we use reinforcement layer of glass fiber, fiberglass embedded in polyethylene, or we use steel wires embedded in polyethylene, which are known as reinforcement tapes. There are other companies in the market that also use glass fiber. They use aramid fiber. Steel strips, right, also are being used. So depending of the brand that is being used and depending of the technology available, a lot of different kind of technologies might be seen in the market, but the concept is the same, right? It's just to provide a product that has a good resistance against the potential corrosion that might be seen during the operation, which move us to the next slide. Please, Ron, will you please be so kind to move on the next slide? So the difference that might be seen in the market and pointed out of what will be the concept of this conversation, which will be the CCUS, right, is what kind of coatings, right, or protection layers I will have in operation in conjunction with the HDPE, right? As you might see in the graph, right, we normally produce pipe that has a co-extrusion, and that co-extrusion might be produced with a layer of polyphenylene sulfide, which acronym is PPS, right? And that goes with a tie bond layer to the HDPE or PRT, depending on the temperature that we are looking to see in the product, right? This layer of PPS can be also substituted by nylon 6 or nylon 12. For a little bit of chemistry, nylon 6 means six carbon atoms, and nylon 12 means 12 carbon atoms. So then we have the reinforcement, and then we have the outer jacket, right? The difference with these configurations is just to provide a material that stands against temperatures between 65 Celsius to 82 Celsius, which is our case, right? And also stand with different kind of connections with fluids. In this case, the PPS liner and the polyamide liner has a different configuration in terms of chemistry, right? As you might see, right, the configuration of the polyamide is structured in a way that has more molecular space. I will not get into the bonding and the deep chemical of the polymer. The point here is that the space available between the molecules in the polyamide is bigger than the PPS. In the PPS, we are speaking around 0.5 nanometers. So the space is really small, which that means that at this point, the fluid that might pass through, meaning permeation or diffusion of fluid, is really small. And that places us in the next point of our conversation, which is something called permeation. What is the permeation? The permeation is the process in where a fluid passes through a membrane, right? We got to remember all polymers, it doesn't matter which brand, which company, and which kind of polymer has certain level of permeation. Let's take, for example, everyone here in this audience has been taking a coffee once in their life in a plastic cup. If you leave it for a little bit, that plastic cup will be stained by the coffee. That is called diffusion, right? If you do it in the porcelain cup, that stain will disappear, while in the plastic it's not. So that happens in all polymers. So there is with the difference of polymers that are available in the market, there are different kind of permeations that will be allowed through the polymer based on two factors: the size of the molecule that is going to be transmitted across the flow, and also the temperature that is going to be seen by the polymer due to the contact with the fluid. What does that mean? In terms of the temperature, at the time that I have higher temperature, the polymer will have an increase, not a bigger. It will have an increase on the molecular space. So the level of permeation will be increased with the temperature. This is what is being shown in those slides, in this slide and these charts, right? You will see in your left, right, a comparison between H2S, CO2, and CH4 at different temperatures and in different polymers. And it's evident the difference between conventional HTP and PPS, which is almost negligent in most of the cases, right? We could move to the next slide, Ron. Once we understand the fact that the permeation will prevent the movement of harsh molecules across the barrier, right? This means that you need to control the source fluids. And these pipes needs to connect it from pipe to pipe or pipe to facilities with a metal connection, which is called fittings. These fittings are done in different kind of material to stand different levels of soreness depending on the fluid that is going to be transported. So in this case, we have a different kind of steels, which are carbon steel protected with zinc. We also have carbon steel protected with FBE. FBE stands for fused bond epoxy. We also have 316, 316L, and also 2205. And lastly, we have some applications in where Inconel 625 might be applied. It's not listed here because it's very uncommon. And also is a jury, right? Is all here knows how expensive might be the Inconel, right? In terms of the connections, the pipe might be in basically assembled with MPT thread, welded ends, or API azimuth flange, right? So that might be seen in the red flange that you are able to see at the bottom of this slide. The connection is done with a special machine that requires an additional session to explain how it works and so on. But the concept that we want to transmit here is the fitting is prepared to receive the fluid that is going to be transported, and the CO2 has some level of aggression on the polymer. So in this case, the 316L or the fused bond epoxy is the application that we are looking to apply when we are doing CCUS projects. So say that I close the chapter with the fittings and I move on the next slide.
Awesome. All right, so we're going to look at the value proposition, which is, you know, the application of the technology in itself, right? So we highlighted initially CCUS being one of the low-hanging applications that we've highlighted, right? Obviously, main concern with carbon emission, you know, it's sort of an offshoot from industrialization, right? We have a lot of say Ghana, we have a lot of oil and gas activity going on, a lot of flaring. We have a lot of CO2 emissions from manufacturing plants, from electric plants, from refineries. And, you know, what the flexible pipe as a product here offers is a transport solution, right? As an alternative to conventional steel. Now, you know, in terms of benefit, the product is corrosion resistant, right? Because we do understand that CO2 is quite corrosive, so that the product offers that that immunity. You know, in terms of adaptability, it is suitable for all terrains, and the flexibility also makes it easy to meander around challenging pathways, and it can be configured based on required temperatures and pressures. Like, and again, you know, I mentioned earlier, you know, circular economy, right? It has a reduced environmental impact overall, because in terms of installation, you know, we require minimal disturbance to the existing whatever the environment, right? Digging smaller trenches, you require to dig smaller trenches because of the connecting process, right? Which we'll show in a little bit more detail, right? And again, the modularity of it is one aspect to look at as well, because you know, we're offering this product is spoolable, so we're able to kind of spool you know, excessive or reasonable lengths on circular spools, and allows us to kind of minimize that number of connections that we're making. So depending on, you know, the length, you have that optionality, and ultimately we are providing that transport conduit for, you know, carbon sequestration, whether it is for enhanced oil recovery fields or for geological formation storage, which can later be used for green methane formation, which, you know, Jose will talk about in a little bit more. But, you know, there are some obvious challenges around, you know, increasing temperatures and pressures, and Jose can give us more insight in the supercritical CO2 handling.
Yeah. Look, one of the key things that we need to understand, right, is one of the missions of the CCUS model, let's say it in this way, right, is we need to reduce the carbon print, right? And that model or that tendency, right, is real. The thing is that we need to reduce the CO2. Nevertheless, during this process, we need to understand how the CO2 is being moved, right, and how the CO2 behaves. So if you see the chart, right, the CO2 might be moved in gas, might be moved in liquid, might be moved in dense phase, and might be moved in supercritical region. So normally the market tends to use two protocols. One could be the transportation with the density above the 800 kilograms per meter, where we are looking to do the transportation in a liquid phase, or do the transportation over the bubble point of the CO2 mixture. And when I say mixture, is because normally the composition of the CO2 is not 100% pure. Is something that becomes from a process that normally will give you 90% of purity, and all the rest 10% will become with nitrogen, will become with some traces of water, which creates some kind of harsher bottom during the transmission. So this kind of things needs to be prevented during the planning of this, right? So to close the comment in terms of the supercritical CO2, the driver here is also economical, right? Because as is understood from the zoom-in that Ron just did a few seconds ago, the supercritical region and the dense region for CO2 transportation requires that the system is energized at high pressure to keep the density constant during the operation, because the CO2 might change from phase really easily, right? So this demands a lot of energy, right? So based in that, normally the projects that we are seeing today are in gas phase, because you have a more window to work, and even the amount of CO2 that might be transmitted is less in terms of cost is something that is attractive, right? There are other projects being assembled in dense phase, but the reality behind of this is the cost. So this moves us to the next slide that has been shown at this moment. What is the process to follow up to capture the CO2? There are many processes right now. There are many startups at the moment. Actually, we have one in where we are planning just basically breathing the air and capture the CO2. This is a future technology, but what is available right now? What is being used at this moment? What is existing at this moment? The CO2 storage can be done through a chilled ammonia system unit. And this system basically uses an ammonium carbonate to capture, and this ammonium carbonate reacts with the CO2 and it basically takes out, right? And once the process is done, the efficiency of capture is around 90%. It's a really good process. So once that process is done, it goes on pipelines to the storage, which was the point that was mentioned by Ron. Ron, do you want to complement something here, please? You are on mute, please.
No, Jose covered it for the most part. But like I said, you know, the application here is not so much of the technology. The flexible pipe is complementary, right? And offers that permeation resistant barrier. So in an offshore or an onshore carbon storage application, you're not compromising on safety or any aspects looking at using the flexible pipe. Okay. All right. So the next slide. So green methane, Jose, do you want to talk on this further?
Yeah, for sure. In the case of the green methane, right, this is a sub-application of what we has been shown, right? Once the gas has been sent to the reservoir, right, there are different kind of business that can be conducted from this point of view, right? So the last slide shows something that for us might be called enhanced recovery, right? We use the CO2 to give more power on the reservoir, and basically that additional power will help to produce more oil, right? But in other occasions, the well has been depleted, right? So there are companies as Haichico in Argentina that become really smart on thinking how these depleted reservoirs might be used, right? So could you please go back? Sorry, thank you, Ron. So what this company is doing, right? They use the process to inject CO2, and at the same time, they are using the eolic energy to do an electrolysis on water source to produce hydrogen. That hydrogen is being sent also to the reservoir, and they inject CH4, methane in this case, to create the seed in the reservoir to produce CH4 called green methane. So this green methane is acquired with the time because it needs the reaction inside of the reservoir might need time, right? But this well, and this project is being produced. We are going to supply the slide. If you want to read more, the link to access to the information is in this slide. Also, and lastly, to close this conversation in regards of this slide, also the H2, the hydrogen, right, the lines has been or are planned to be in use to store hydrogen. This is something that is a project that is ongoing, and is something that is cataloged as a work in process. But that is part of the future activities that might be seen also on non-corrosive flexible pipes. There are other projects or other CO2 applications that being seen in this slide, right? The CO2, once reach 99% of purity, might be used for refrigeration, right? This refrigeration project has been done in Switzerland. I had the opportunity to install this project. This project was done basically to energize and give a cooling system of 800 kilowatts in between heating and 600 kilowatts of cooling in between the three buildings, right? We install a 3-inch Thermoflex Plus pipe, which means a PPS pipe. The project is up and running. This was installed in August 2021. And so far today, the level of permeation that has been produced on this project in the last 3 years, it were way below than 1%. So let's move on the next slide. You might be see how the project was installed. It was extremely challenged. But the thing here, aside of show how the flexibility of the pipe might be helped to acquire confined spaces, right? It also helps to do a precise job, right? We're really proud to say this. In this case, this job was done with a tolerance of 1 centimeter between line in order to be able to be aligned with the equipments that are going to be the reception and the processing of the CO2. So say that I finished the comment here. This project is up and running in Switzerland. You could search it also with these guys called Exergo. Next slide, Ron, please.
Yeah, so to that point, right? That what that exhibition, I just add to Jose's point is, you can see the team working and the flexibility and adaptability of the product being used for that scope of deployment, right? It is a confined space, but the product still offers the same operational integrity that you would get from a steel pipe without the mechanical restrictions, right? So that's something good to highlight. Again, the other aspect that we want to talk about is the carbon footprint, right? In terms of using, the manufacturing and installation, right? I mean, a greenhouse emissions life cycle assessment, was done looking at, upstream activities to downstream activities involved in making, equivalent quantities of steel versus non-metallics, right? Now, it was kind of documented that about 102 metric tons of CO2 equivalent, was used to produce, from manufacturing to installation of non-metallics versus 410 metric tons of CO2 equivalents for metallics, right? Which essentially is a 75% reduction, switching between the two products, right? The other critical aspect to consider is that, in a lot of scenarios where operators or customers are installing pipeline, there is a bit of a disincentive to refurbish or repair these lines just because of the difficulty in handling and the machinery required to do the excavation and also decommissioning, right? But using flexible pipe offers that fairly flexible remediation solution where it's required. So that is just something to highlight, right, for upfront. From a manufacturing standpoint, Jose, do you want to touch on this?
Yeah, look, I guess it's really important to highlight one point here, right, which is the fact that the flexible pipe will not replace the rigid pipe, right? The rigid pipe has a market that has been established from a long time ago, and they are able to produce pipes up to 16-inch, right? And I guess now they can do more, right? But the flexible pipe covers an inch that goes up to 8-inch, 10-inch, more or less right now. And the idea at this point is to show the understanding around the process that we are going to show at the second is the energy that is being used also produce a carbon, it also produce or also give the trace of a carbon production, right? So when we compare the rigid pipe with the composite pipe, there are processes that are completely different in terms of timing. And I'm really emphatic and really specific on this concept. The rigid pipe, seamless pipe requires around, in the total cycle of production, about 10 months. 3 to 4 months to do only the pipe rolling, finishing, and the system loading. Another 3 to 5 months to finish all the requirements, meaning welding, calibration, CNC, passing, final coating in some cases, right? And the flexible pipe, in terms comparing the same diameter, might be 1 to 2 months, depending on the window available in the manufacturing plant. And the total cycle with installation might go between 3 to 4 months. The point here is when you compare both processes, right? It's fair to say it's not the same, right? The amount of heat that is generated on the steel process is way over than the flexible pipe because it's not the same melt steel at 1,100 Celsius, then melt flexible pipe, which is HDPE, goes a melting point at 135 Celsius, right? So the amount of energy required in both process is way different, right? But again, the idea here is that the flexible pipe is planned to cover some things that are not part of the process of the rigid pipe, right? It's well understood that the CO2 pipe, the CO2 pipelines right now are becoming a real market for the RTP pipes, because normally the corrosion that might be affecting the steel pipes is high when we are speaking conventional seamless pipe, right? If we go in a 3/16-inch pipe, well, the corrosion will be minimized, but the cost is extremely high. So it's a balance between the capability, corrosion, and the cost associated to the project. So the next slide, please, Ron.
All right. So to talk about the installation aspects, right? So we talked about manufacturing, installation, like the video that we showed earlier, it's critical to highlight again the economics related to installation, right? So to install flexible pipe, you do require a smaller crew. The image that we showed earlier, we're looking at, I think we had about a three-man crew installing almost a 2.8 mile pipeline versus traditionally you having a 8 to 10 man crew doing the same scope of work, right? And you will require different level of skills in terms of welders, fitters, pipe trenchers, crane operators. More so that the logistics installing flexible pipe versus steel is significantly different, right? We see a 60 to 80% variation in costs going one option versus the other, right? Jose, do you want to add anything here?
Yeah, I guess just to finalize this slide, it's very important to highlight that the amount of machinery that is needed to do the installation process also plays a huge difference in terms of the carbon print, right? Normally, to do the installation of the RTP, the trench will be the same. It's the same machinery, the same preparation. But by the time that you need to lower the pipe, you need to deploy the pipe, the amount of equipment is a difference. It's way different, right? Because normally the flexible pipe can be handled even by hand, while the rigid pipe, yes or yes, you need cranes, you need loaders, we need the welding machines, and so on. So in terms of difference, comparing apples to apples, in this case, the 16 tons versus 80 tons, what was an analysis done considering a 4-inch pipe at 5 kilometers length, right? So say that, I close the comment, Ronnie, back to you.
Yeah, so again, the expected, one of the key things to look at in terms of, the economy of it is the time saving, right? We look at the installation velocity, say potentially looking at a 1 kilometer length line, right? We're looking here at three scenarios, installing like a 4-inch, 6-inch, and 8-inch of reinforced thermoplastic compared to steel, right? If you look at the installation velocity, you see steel pipe taking up to about 3 days versus the thermoplastic taking averagely about 2 days, and in some scenarios less, right? When you advance to larger size piping, you see a significant change in the speed of deployment, which is a critical cost savings for any kind of project, right? It's a cost savings in terms of the cost to install, and it's also a cost savings in terms of the time it takes to bring the project back online, depending on whatever the fluid to be transmitted is. So for instance, if it's an oil and gas production, you look at the days, the opportunity cost of no producing daily, and you see the benefit using flexible versus steel. But again, I just reinforce what Jose said. It's not a one size fits all. It's critical to look at, which applications have an advantage using flexible versus steel, but it is a comparable alternative for most scenarios. So something to highlight. Jose, do you want to touch on this, the rehabilitation?
Yes. Well, Ron gave a flavor, right, a couple of slides ago about what happened with the flexible pipe rehabilitation, right? The thing here is that part of the carbon print reduction goes also on what is the network installed in every country around the world. And normally that network is related with rigid pipe. So when we compare the fact that we need that we have a pipe that is basically auto service, and sometimes it needs to be decommissioned, right? Sometimes it's condemned that is closed, right? But some other occasions you need to decommission the line, that is expensive. You need to substitute the line, that is also expensive. So the rehabilitation also comes into play to reduce the carbon print, because basically what is done is just to pull through the flexible pipe inside of the 16 pipeline, and due to the flexibility of the line, will allow the pipe pull through with no issues. And then the minimal needs will be the connections between pipe to pipe that, when compare the 4-inch, right? Normally a 4-inch might have around 600, 650 meters, depending on the diameter of the pipe per reel. You will see that in a few seconds, right? And well, the amounts of connections that are needed are few. So that, in terms of the carbon print, is in where the math will become an economic advantage, right? And these videos might be shown what we are speaking about. You will see in the first video how that a inch pipe is being deployed. As you see, is really easy from the point of view of the machinery, the truck, and the reel that is being used, right? And the welding is absent in this case. So that is part of the difference of the process that is being done. As you see, the trenching might be the same, right? And other project that is shown below, it is 4-inch. That is an installation also done in the same way, is pulling the pipe from the reel, right? Spay off the reel. But to finalize my comment here is this process demands way less equipment when compared with the conventional technologies. Again, we want to reinforce the idea. We don't want to create or seed the fact that the RTP pipes are better than the steel. No, each pipe complements its own market. The point here is how the carbon print reduction might be achieved in case that there are companies that are starting to demand that in tender process. We are seeing that before. And sometimes, if that is the case, these kind of technologies might bring a solution, an economical solution, to meet these kind of criteria that are being now placed on the table from different kind of end users. So say that, Ron, back to you.
Yeah, no, so, just to show a little bit more, this is another application where we're going, we're installing a 8-inch pipe versus 12-inch rigid pipe. Obviously you do have the size advantage, but you can see the manpower and infrastructure requirement for installing one versus the other, right? Again, at the moment, like Jose mentioned, we're going up to, I think, up to 10-inch maximum for 8-inch. Steel does have the variability, but the handling challenge and constraint presents its own challenges. So that is just something to look at. The safety elements, operating steel versus flexible, exponentially vary. So it is something to look at, right? This whole presentation, just to highlight again, has been based on onshore application of composites. We've looked at some offshore applications. I think, if we were to go into the offshore aspect of it, that might require probably an additional hour, but we've tried to keep this digestible based on the offshore application scenarios, and we hope this has been of some value to you. So again, thanks again for the time, and we're happy to take any questions you may have. Appreciate it.
All right, thank you, Ron, and thank you, Jose, as well. From the little I have gotten from this presentation, is telling us that flexible pipes are cost effective for application in our industry. It has a faster installation time. As compared to regular steel pipe that you may have to have a lot of connections. This one, the connections are fewer. So the inspection regime will also be lower. With the regular steel pipe, you need to do a lot of welding and NDT testing, but all these are eliminated by the use of the flexible pipeline. And then it's mobile, it's also environmentally friendly, more sustainable. Thank you very much. I would open the floor for questions from anybody. We can kindly raise your hand and I will call you, then ask the speakers the question. Any question from anyone? Okay, maybe I will start. Okay, so Rap has his hand up. So Rap, can you go ahead?
Rob, you're on mute if you're speaking.
Yeah, unmute yourself and speak.
Hey, Rob, you want to go ahead?
If you are speaking, you are muted.
Yeah.
You can also write in the chat,
Okay.
right? We read if necessary, right? There's no problem with that.
Yeah, sorry guys.
We can hear
me?
you now. But...
Okay, yeah.
Yeah, we can hear you, yeah.
Yeah, Rod, good afternoon. Yeah, I'm Robert from Tetra. In speaking, maybe I may have missed at some point, but in terms of decommissioning, right, and how much of the material are you able to recover? Because with standard steel pipe, you're able to recycle most of the components, right, into as raw materials. But in this, what's the added advantage you have? Because once you move into polymers and plastics, then it's also now the world is all about reducing, carbon footprint. So yeah,
that's a good question, Ron. Let me take this one, right? There is an important point here, right? Normally, the flexible pipe and the rigid pipe, what are used to move oil, those pipes, in terms of the commissioning, has a different process, right? Normally, the polymers that are being in contact with H2S, CO2 must remain in place. This is really important to remark. It has been used with a different kind of fluid, it's water and so on. There's no problem. It can be decommissioned, right? The pipe can be stripped, and the HTP section, right, might be treated again. But it can be used in a different application. It cannot be used again on the flexible pipe because the API 15S demands that all the pipe that is being produced cannot use recycled material. It needs to be used from pristine HTP, right? So to conclude, my response basically would be depending of what is demanded by the customer, right? In some other part of the world, the decommission is part of the process at the lifetime of the pipe. In others, the pipe is shut down at its close.
All right, thank you.
You're welcome.
Thank you. Any question from anyone? Okay, so my question will be on when you install, do you have to do inspection like other pipes that you may have to do inspection around the pipeline? Does it require inspection during inspection?
Yeah. Ron, let me take this one, right? In terms of this inspection, right, the way of inspect the flexible pipes versus the rigid pipe are way different, right? Because in the case of the flexible pipes, when compared with the rigid pipe, the flexible pipe cannot receive a magnetic fluke leak, for example, right? Because the density that is going to be read is basically a polymeric layer. So the transmission of the signal will give nothing, right? So the other side of the coin is that those tools are quite invasive from the point of view of the structure of the tool. So it may damage the pipe inside. Remember that we are treating with a polymer. So there are other kind of technologies right now to do some sort of inspection. The first one is called Ingu, right? This called Ingu is a small valve, 2-inch, and it have a geoposition, pressure reader, and a temperature reader. So it sends with the stream of flow, and it sends if there is any change of pressure and temperature in the stream. So what does that mean if you have a small leak or you are being robbed? Because that is something that happened, at least I see it in Colombia, for example. These guys are magicians, right? And they introduce a tool in the pipe and they just milk out the oil. So you are able to say to locate and take over about where that process is being done. So you repair the pipe and so on. Other processes that are being used to do the inspection, there are some strips that read a voltage change, right? And that voltage change is basically based on the fluid that is going to be in contact with that strip. So if, for example, there is feeding leak, right, for some reason, a earthquake or land displacement, and there is a drop of oil and touch the strip, that will immediately give a signal out to give the positioning where this might be happening.
Yeah.
So those are more or less the technologies that are available to check the flexible pipe. For sure, there are others around, which is visual check, getting in, getting out, the flow meters, just to check that the volume that is being transmitted from side to side are equivalent, right? And to close my question, then the conventional tooling used for the rigid pipe inspection cannot be used on the flexible pipe inspection. So I close my comment. Back to you.
I mean, just to add to that point, right? So we're not necessarily doing post-installation testing just because of how the installation process goes about. We're essentially doing, as can be seen from some of the videos, code forming of connections, and in some instances, flanging connections together, right? So we're not, we're not necessarily welding. We typically do hydro tests with fluid to just test check the sealing integrity of the pipe, structural integrity of the pipe as well. And we usually we're testing these pipes up to about 1.5 of the maximum operating pressure of the lines, right? So regardless of what the customer intends to operate the line at, we're typically testing above the test pressures. And the good thing with flexible pipe is sometimes we do find failures, bursts, ruptures as a result of handling because of the flexibility. That is a challenge it presents. But in that scenario, you have the optionality to quickly splice the line, right? So you can quickly replace that section that has failed with a strip of line, regardless of the length, and splice that section with a fitting and put the line back online. So it gives that I guess flexibility to test and also to remediate in event of any failures.
Oh, all right. Thank you. SP Ghana, who you want to go ahead?
Hi, it's Joseph here.
So,
Yes, I want to ask a question. Yeah. So with the flexible pipes, what are the likely failure modes, and what kind of limitation does it impose in terms of its applications?
Yeah.
well,
yeah. The failure mode is the communities, right? I see it before in many places. The pipe is in operation, and sometimes the agricultural activity introduce a lot of what we saw as a failure, right? They are cleaning, dragging, cutting the bushes with a machete, right? They cut the pipe, right? So that is a problem, right? And we are trying, when we do or perform the assessment to do installation of flexible pipe, and we normally see that if there is a community around, we recommend to bury the line. And normally we also request to tape at least 30 centimeters over the pipe to prevent someone that is doing some excavation to be aware that there is a pipeline below, right? Also now is being introduced a wear cable that it normally can go with the flexible pipe, not inside of the flexible pipe, over the flexible pipe, used to, if there is a metal detector around, it can check that the pipe is available in case of, right? But that is the first failure mode, right? The first thing is the third-party contact, right? Other failure mode that might be seen on generally on flexible pipes, right, might be associated with the volume of GOR, right, that are present from the reservoir and moving across the pipe, right? So if the pipe, normally all pipes in the market might have a venting point, right? If for some reason during the installation the technician didn't place the vent hole, whatever technology is used depending on the brand, the pipe might have some blister, right? That is the second failure, the second failure mode that can be seen on the flexible pipe. Important, the blister will not stop the operation of the pipe, but it's not seen well, right? So normally all companies that offer this kind of pipe has a venting procedure to be sure that the gases that are produced from the normal process of transportation of fluids are properly evacuated during the transmission process. I close my comment.
All right, thank you. Thank you, Joseph. Just a slight question. How does this perform with wax and sand erosion during transport?
Look, also there is a really important question, right? Because normally that will be depending on what kind of internal liner that you are going to use, right? Normally, if you have a well that is tending to produce a lot of sun, right? A lot of sun, PPS will be your ally to control the sun, because in the bendings that you might have during the on your right of the way of the pipe, right? In each bending, you will have an erosion problem, right? That might be accelerated if you do not control the vent radius and how the pipe is being deployed. But with the material, you will also enhance the durability of the project. In the terms of the wax, the nylon 12 and the nylon 6 are the right polymers to control that. You don't need to go on the PPS up to, it's extremely necessary, right? And that is a relation of cost. Again, we speak around that a lot because normally we think in the fact that the projects must fly basically. So to control paraffin, wax, and asphaltenes, normally the PA12 is the right polymer to control that. The molecule is too close, right? And when that process is happening, normally the wax gets on the topography of the polymer, but it do not get in. So by the time that you wash off with hot water, it just get clean immediately, right? And it disappears. It's really easy, for sure. The thing here is that we are not saying that with the PA12, the problem will disappear. No, it will be reduced because with time to time, you need to do the cleaning of your well and you need to do the cleaning of your facility. What will be enhanced here is the amount of energy that you need to use to do the total cleaning, because it's not the same to do a cleaning of a plug line than a line that has a certain wax level that will be easily removed with the hot water. Right.
Thank you.
So,
thank you, Jose. Thank you.
That
was insightful. Thank you for bringing us knowledge on flexible pipelines and its operations. We're grateful. SPE Ghana is grateful. I will call up Joseph to give a closing remark.
All right. Thank you, Dominic. And thank you once again to our speakers for what has been a very insightful discussion on flexible pipes, about the operational efficiencies that it brings, as well as how it is helping us to transition towards a low carbon economy, which is something of a global interest. I think we've all learned a lot, and we go away with quite a number of good takeaways. So thank you once again, Roland and Jose, for that discussion. So on the 2nd of November, there will be another discussion like this on being security conscious in the digital world. So the flyers will be out very soon. We'll have yet another insightful program from SP Ghana. And then on the 10th of November, there is one in collaboration with ASEP on finding a sustainable path to net zero the African way. So that will both be online and in person at ASEP. So the details will be out pretty soon. I would like to remind everyone as well to follow us on our social media handle, SP Ghana, on all social media platforms. And also, please do renew your SP memberships. It's important. It helps to keep things going. And we'll see you again on the 2nd of November for the next program. Oh yes, and then this weekend there's a walk, the breast cancer walk. So please, if you are in Accra, we are meeting at 8 a.m. at the Lincoln School. Please do come around and let's do something good for each other. Yeah. All right. So thank you very much, and see you again soon. All right. Thank you, Roland. Thank you, Uze. Thank you so much, guys.
Thank you so much.
All right.
Appreciate your time.
Thank
Bye.
you. Appreciate the time.
Thank you. Thank you,
Good night,
guys.
everyone.
Thank you.